everybody. So let's start the statement. Start with the statement of this Cauchy Integral Formula. Then we shall move to the proof of this formula. What does it say? It says that if a function f is there, which is analytic in a simply connected domain, maybe capital D, bounded by a rectifiable Jordan curve C, this kind of curve C, and it is continuous on C, on this curve, then this f of z is equal to, this can be written as 1 by twice pi I integral over this curve C, f of xi divided by xi minus z dxi. Over here xi is a complex number, mind it. Let me draw this one. And z, what is z? Z is a point within this domain D. Let me draw this picture for you. Suppose we have a curve as per the statement. We have this kind of region. We have this kind of simply connected domain. This is the domain D, and this is bounded by a rectifiable Jordan curve C. This is a rectifiable Jordan curve C. And what is the function f of z? It says that f of z, this function, this is a function f. This function f is analytic in this domain D. So we can say that f is analytic within D, within this domain D. Okay, f is analytic in this simply connected domain D, and this domain is bounded by this kind of curve C. And it also says that this function is analytic within D and it is continuous on C. So we can also say that this function f is continuous on this boundary C. In that case, if this is any point z within this domain, in that case we can say that for such point, this f of z, this f of z can be written as 1 by twice pi I integral, that would be a line integral on the boundary C, f of xi divided by xi minus z, xi minus z dxi. So integral is taken over xi. That means xi are actually the points on this curve and on which the integral is taken. So we can say that the point xi over here, this might be the point xi, the position of the point xi. Xi is any arbitrary point on this kind of boundary C. All right. So this is the statement of Cauchy integral formula. Over here, xi is any arbitrary point on the boundary of this domain D. That means the boundary C on this domain D. So we shall have to prove this result first. Now, how to prove this result? We are given that the function is analytic within this domain. So as because it is analytic, it must be a continuous function within that domain D. So by continuity, what is the meaning of continuity? By epsilon delta definition of continuity, we can say that for each epsilon greater than 0, there exists a delta greater than 0, such that modulus of this kind of quantity, modulus of f of xi minus f of, rather let's not write xi, let's rather simply write um, okay, let's write xi because z is already there. Z is particular one point, xi is an arbitrary point. So f of xi minus f of z, hmm, f of xi minus f of z, that is less than epsilon. Over here xi is a variable number and z is a fixed complex number. Okay, so f of xi minus f of z is less than epsilon whenever modulus of z xi minus z is less than certain delta. Hmm. So over here you see we will get certain this kind of delta neighborhood. Hmm. And within that delta neighborhood this relation should hold. Now let me just elaborate this zone, this delta neighborhood. Hmm. Let me make it a little larger picture. Hmm. Say maybe this is the total domain. So this is the total domain D. This is the total domain D, and over here suppose this is the point Z, and what is delta? We got this kind of delta neighborhood. This is a circle. This much is equal to the value delta. Now we consider a smaller circle around the point Z. We consider a smaller circle, this kind of circle, having radius say rho. Then you see over here for any point, if you consider any point xi on this kind of smaller circle, then what would be the equation of the circle? The equation of this smaller circle would look like this, that modulus of xi minus z, this is equal to the radius rho, or in other words, if we remove the modulus, we can write it as xi minus z, that is equal to maybe rho into e to the power of I theta, where 0 less than or equal to theta less than or is equal to twice pi. Got it? So our discussion will be confined within this smaller circle. Our discussion will be confined within this smaller circle. Let me write the picture once again, because I have to remove all this. Let me remove it from here. I think that would be much more better. I don't know whether it is possible or not. Yes. Let me remove this larger circle. Now let me remove this delta as well, because we don't need this delta right now. We don't need this delta. So we have only this kind of circle, and within this kind of circle, you see, if you look at this picture, then this region, this region, let me draw or shade this region. You see this blue region. This region will be a doubly connected domain. This region will be a doubly connected domain. This one. This region would be a doubly connected domain. Okay, now if you apply the Cauchy integral formula on this region, over here you see z is the point, and z is any interior point. So on this region, if we apply the Cauchy integral formula on certain function which is analytic, which one should we consider? Now in this zone, if you consider any arbitrary point xi, then of course this xi is different from z, because z lies inside this circle and xi lies outside this circle. So we can always say that yes, xi is different from z, or xi is not equal to z. So let's we can say that this expression xi minus z, this expression is always analytic within this zone, because within this kind of doubly connected domain, xi and z, these are two distinct numbers. So you can say that within this kind of doubly connected domain, this 1 by xi minus z is an analytic function. Again, we are given that this function f of z is analytic within this domain D. So within this doubly connected domain as well, we can say that this function f of z is analytic, and therefore if we multiply this quantity by f of z, then what we have, we simply have this kind of, not f of z rather, because we should write f of xi, not f of z, because z is over here a fixed quantity, a fixed number. Xi is an arbitrary number, so we should write f of xi. All right, so let's multiply it by f of xi. Z is a fixed quantity. So this kind of expression would be analytic f of xi divided by xi minus z. This kind of expression, this kind of function will be analytic within this kind of doubly connected domain. And therefore you can apply Cauchy integral formula on this kind of function f of xi divided by xi minus z for this doubly connected domain. And for the sake of discussion, we considered this boundary as C, and let us consider this circle, this inner boundary, inner circle. Let us write it as C1. Then by Cauchy integral formula, what we can write by Cauchy integral formula, we can simply say that integral of this f of xi divided by xi minus z dxi, that must be is equal to integral over the curve C1 of for the same function f of xi divided by xi minus z dz. So we got this result from Cauchy integral formula, from not Cauchy integral formula, from Cauchy's theorem. From Cauchy's theorem, or Cauchy-Gauss theorem, whatever we call. In Cauchy's theorem, we have this kind of result, that integral over C, that must be is equal to integral over C1 for Cauchy's theorem for doubly connected domain. Bounded by C and C1. So we have this type of result, integral over C. Actually what we get, this kind of integral on the boundary is now converted into an integral integral over the smaller circle. What was the smaller circle? This is the smaller circle. This curve is actually the smaller circle, and that is actually a circle, not any arbitrary curve. C was any arbitrary boundary. But now C1 is any smaller circle, and what is the equation of that kind of smaller circle? This is the equation that chi minus z is equal to rho into e to the power of I theta. This would be the equation of that kind of smaller circle C1. So we can say that where C1 is the circle given given by say what was the equation that chi minus z is equal to rho into e to the power of I theta. So let me write chi minus z is equal to rho into e to the power of I theta, where 0 less than or is equal to theta less than is equal to twice pi. So this was the circle C1. Now everything we shall perform on the circle C1. Over here everything has to be performed on the circle C1. So let us designate this equation by equation number 1. So this is the equation number 1. Now you see over here this right hand side expression, if we divide both sides by 1 by twice by I, we shall have this type of relation like this. And now we shall continue with this integral. Let's copy this part and paste it. What we have, this expression can be written as, you see, this can be written as f of chi minus f of z, f of z plus f of z. Next, copy and paste this relation. You see, this expression can be decomposed further. This can be written as like this: f of chi minus f of z divided by chi minus z, and the remaining portion can be written in this fashion: plus f of z divided by chi minus z. Now let's discuss this integral first. What is the value of this integral? So copy and paste it. Now you see over here this f of z. This is a function or a quantity dependent on z, not on chi. Chi is the variable quantity for this integral. So we can take it outside this integral sign. We can write it in this fashion. Now on this curve C1, what was on the C1? C1 is equal to this kind of curve chi minus z is equal to rho into e to the power of I. So if you put chi minus z is equal to rho into e to the power of I theta over here, rho into e to the power of I theta, what would be d chi? D chi would be is equal to, what is d chi? Let me write it over here. D of chi would be is equal to rho into e to the power of I theta into I d theta. Okay, so this is our d chi. So in place of this d chi, let me put this expression. So now integral is converted as an integral on this parameter theta, and what is the range of this parameter theta? 0 to twice pi. So now the integral should be written as 0 to twice pi. Now you can check over here. You see this row and this row will get cancelled. This e to the power of I theta and e to the power of I theta will get cancelled. So in the next line, we can cancel this expression along with this expression. So we shall have I into d theta integral from 0 to twice pi. So its value is equal to I into twice pi after integration. Twice pi I would be there. I into twice pi. That would be the value of the integral. And you see this twice pi I will get cancelled with this twice pi I. So after that, we can simply write this expression as if we cancel this twice pi I and this twice pi I, we shall simply have f of z. So this is the value of the second integral f of z. So the second integral is equal to f of z, and on the left hand side we have 1 by twice pi I integral over c1 f of xi divided by xi minus z dj. Alright. Now if I shift this f of z on the left hand side, then what we have? So let me copy this left hand side first. This is the left hand side. This expression is equal to this expression. This much we have. Now I am going to shift this f of z on the left side. So we shall have minus f of z is equal to this kind of expression. Alright. Now we take the modulus. Now if we consider the modulus over here, in the next line, let me take the modulus. This is the modulus. In that case, what we shall have? We shall have modulus of this kind of expression into modulus of this kind of expression. Now modulus of 1 by twice pi I. This is nothing but is equal to 1 by twice pi, because modulus of I is equal to 1. So let me just remove the modulus and write it simply as 1 by twice pi. And this is the modulus of the integral. And you see, modulus of this kind of integral, that can be written as less than or is equal to modulus of let me just reduce this magnification. So over here no, it is not working. Okay. Now you see over here, this integral, this modulus symbol can be written in this way: modulus of this f of z into modulus of this kind of dj. Okay, and therefore you see this this can also be written in this fashion, that modulus of this numerator divided by modulus of this denominator. And what is this? Modulus of this numerator, you see, within this kind of curve C1, let me come back to this picture. What we had, we actually had this kind of larger delta neighborhood, and within that delta neighborhood, this relation was true that f of xi minus f of z is less than epsilon whenever modulus of xi minus z is less than delta. That means inside this kind of circle, or we can say on this circle C1, because this is a circle which lies inside this delta neighborhood. So we can say on this curve C1, this kind of relation, that f of xi minus f of z less than epsilon, this kind of relation should hold. F of xi minus f of z less than epsilon, this kind of relation should hold. And therefore we write over here in the next line, we can say that the left hand side, this left hand side will be less than or is equal to how much? This this expression 1 by twice pi I integral over C1, and this over here, this numerator, let me just copy and paste it. This expression is less than epsilon, so that would be less than epsilon, and therefore we shall have strictly less than inequality, because it is this expression, this numerator is f of xi minus f of z. This is strictly less than epsilon. Over here, strict inequality appears. Got it? So we can say that this is less than epsilon. Now what is xi minus z on this curve? we already considered that this chi minus z is equal to rho here. So this chi minus z over here, this chi minus z is equal to rho. And now this expression is actually does not depend upon this variable xi, and therefore we can write this expression as equal to, we can just keep it outside the integral symbol. So this is modulus of dxi on this curve. And what is this? This is actually the length of the curve C1. Modulus of dxi, integral of modulus of dxi, or dz, whatever you call. Z, we are not using dz because z has been taken as a particular point over here. So xi is an arbitrary point. So this value, this integral is actually the length of the curve C1. And what is this? The length of the curve C1. This expression, the length of the curve C1. C1 is the curve. This is the curve C1. This is the curve C1. C1 is the curve with radius rho. This is a circle with radius rho, and therefore its value, the length of that curve would be is equal to, length of the curve would be is equal to twice pi rho. Got it? And now we can cancel this twice pi, this twice pi, we can cancel this rho, this rho. So on the right hand side we shall have simply epsilon. So what we have, let's summarize this result. We have this left hand side quantity is less than any arbitrary positive number epsilon, and that would be possible as because epsilon is arbitrary positive number. So if we now take the limit as epsilon tending to 0, in that case we can say that this expression will be equal to 0. This expression under the modulus symbol, that would be is equal to 0. So we can say as epsilon is arbitrary, we have the only conclusion we have is that this expression must be is equal to 0. And what does it mean? It means that this f of z must be is equal to this integral. And if you look at the equation number 1, this integral 1 by twice pi I integral over c1 f of xi divided by xi minus z dz. This integral, if you look at this equation number 1, this integral is nothing but is equal to this kind of integral where the integral is taken over the curve over the boundary c. So we can simply write this expression by equation number 1, and therefore we finally have f of z is equal to 1 by twice pi I f of xi divided by xi minus z dz. So that is this completes the proof of Cauchy integral formula. This is the Cauchy integral formula for simply connected domain. There is a corollary. There is a corollary, and this corollary is known as Gauss Mean Value theorem. Mean Value theorem. What does it say? It says that if f is analytic on a domain D, if f is analytic on the domain B, and if the circular region the circular region modulus of z minus maybe some constant value, maybe any complex number a or z0, whatever you call, less than is equal to rho is contained in D, in this domain B, then then what we have, then it says that f of this a, this f of a will be represented in this fashion, that 1 by twice pi integral from 0 to twice pi f of a plus rho into e to the power of I theta d theta. This will be the this is called the Gauss mean value theorem. Now, how to prove this result? Proof is just direct application of this previous Cauchy integral formula. Now, you see over here, let me draw the picture for you. Just delete this one. It says that we have a circular, we have a domain at first. We have this kind of domain. We have this kind of domain D. This is the domain D. Okay. And we have a circular region that is contained inside D, within D. We have a circular region, this kind of circular region, where the middlemost point is taken as equal to A, and Z is any point on this kind of circular region. That's why its equation is Z minus A is equal to rho. In the previous proof, Z was taken as a fixed number or fixed value. Now over here, Z is taken as any arbitrary point, and in place of Z we have this kind of quantity small a. And over here, you see, in that case, by Cauchy integral formula, we can now say in place of Z we have this number a, small a. So we can simply write, what was the Cauchy integral formula? The Cauchy integral formula was this kind of formula, f of Z. So in place of Z we can write small a. So on the left hand side we can write f of a is equal to 1 by twice pi I integral over this kind of curve. You see, you could consider this kind of curve C, you could consider this kind of curve C1, because at the last line, you see, integral can be considered as an integral over C1, or you can also consider the integral over C. We are considering this first integral, the integral over this curve C1. Got it? C1 has this kind of equation, modulus of Z minus A is equal to rho. So let's write it as integral over C1. Now we actually had f of xi divided by xi minus z, divided by xi minus z. But over here, in this case, in place of z, we have a. So let's write it as f of z. Z is now arbitrary. F of z divided by z minus a. In place of dxi, let's write it as dz. So now integral is taken on this smaller region or the smaller boundary C1. Now what is the equation of this C1? C1 has this kind of equation, modulus of Z minus A is equal to rho, and therefore we can write it as Z minus A is equal to rho into e to the power of I theta. Got it? And therefore this implies that dz would be is equal to rho into e to the power of I theta into I d theta. Okay, so this is our dz, and therefore we can write this expression as equal to 1 by twice pi I, 1 by twice pi I integral f of z. Now what is z? From this expression, z is equal to, you see, from this expression we can write what is z. Z minus a is equal to rho into e to the power of I theta Then therefore we can say that this z is equal to a plus rho into e to the power of I theta. Therefore, in place of this f of z, we can write f of a plus rho into e to the power of I theta divided by what is z minus a. Z minus a is equal to rho into e to the power of I theta. So over here we can write rho into e to the power of I theta, and what is dz? Dz is equal to rho e to the power of I theta into I d theta. And now we can cancel this rho and this rho. We can cancel it to the power of I theta and to the power of I theta. So finally what we have, finally you see this I will also be cancelled with this I. So what we finally have, 1 by y pi integral. Oh, what about the lower and upper limit? Over here, theta should vary from 0 to twice pi. I forgot to mention that 0 less than is equal to theta less than is equal to twice pi. Therefore, as because the integral is taken over theta, therefore the limit should be from 0 to twice pi. Therefore, over here as well, 0 to twice pi, that would be the integral. Therefore, f of a plus rho into e to the power of I theta I theta divided by nothing, this much only, because this rho and e to the power of I theta will get cancelled, and this I and this I will get cancelled. So we shall have simply d theta, this kind of expression, and that is the final expression of Gauss mean value theory. So we have this kind of Gauss mean value theory. Okay, this can be given as a short question of 3 marks. So I thought it might be helpful, or it might be used as an exercise whenever you are given certain this kind of proof of Cauchy integral formula, and that is actually a direct consequence. This Gauss mean value theorem is actually the direct consequence of Cauchy integral formula. So that's all for this lecture. Thank you for being with us.